Thank you, Pavel. Now we continue. I cannot repeat it. Wait. Professor Ito, I think you better explain the title yourself because it's very long for me and too difficult. Thank you.
Oh, thank you very much. My name is Kazuhide Ito, Kyushu University, Japan. And today I would like to talk about the international standardization of testing perceived air quality. And okay, hi. The supporting information from in silico model for transport efficiency of acetone from indoor to olfactory epithelial tissues. Okay, since I'm a convener of ISO TC 146 SC6 working group 25 for standardizing the test method for measuring perceived indoor air quality for use in testing the performance of gas phase air cleaners. But I would like to confess the truth. I'm not a specialist of measurement using sub-frontier panels. And then here I would like to introduce some supporting information from the numerical simulation. Especially, I would like to show you the visualization of transient scalar distribution in an enclosed space and visualization of transient scalar transport to the olfactory region in the nasal cavity. Okay. As Professor Paul Walgoki have already explained in detail of the experimental setup and also the fruitful experimental results, but I would like to briefly introduce the outline of the ISO 60044. This is in the final DIS stage, and main principle for in this standard, we described two main principles for measuring perceived air quality. The first one is the perceived air quality is determined using subjective evaluations of acceptability and perceived odor intensity. And the air passed by a panel, assessed by a panel is presented via sniffing device or in the test chamber. And this is the test conditions, and you can see three schematic diagrams of the test conditions. Test room for standalone air cleaners, a test room for induct air cleaners, and test room for induct cleaners, especially for one-burst conditions. And in these test conditions, the panel members shall enter the front space and assess the quality of air presented via sniffing device immediately upon arriving at the measuring point. And measurements shall be made after taking only one sniff of the air, and only one measurement shall be made at a time, either acceptability or perceived odor intensity. And my question is, one sniff is enough for evaluating this index? I would like to skip the detail of the explanation of the olfactory perception, but in my understanding, in order to precisely evaluate the olfactory sensation, we need to conduct a sensory experiment using volunteer subjects. This is, I believe, only way to the evaluation of sensory output. But we have alternative method to provide a supplementary information or supporting information of this subjective evaluation. And then I would like to show some results. I would like to skip this one. This is the history of the development of computer simulated person. And please take a look at. Sorry. Maybe you can see the two animations. The left-hand side animation is the concentration distributions of passive scalar emitted from skin surfaces. And this is assumed to be the bio-effluent from the emission of human body. And right-hand side figures show the carbon dioxide distributions in indoor environments generated from the respiratory system. Our model have already integrated with the gas exchange model at the alveoli region. And you can see some very two important points. First one is the heterogeneity of scalar concentration distribution in this indoor environment. This condition is very special because there is only one human body in the very small room with high ventilation rate, 10 air change per hour conditions. But still, we can confirm the heterogeneity of scalar concentration distribution in this enclosed space. And second point is formation of clearly different concentration distributions for different emission locations. I mean, in case of the skin surface generation, contaminant generation, and scalar generation from beer respiratory system, we can confirm the significant difference concentration formation in indoor environments. And my simple question is, what is the composition of the air inhaled in only one sniff? And in order to analyze the impact of the adsorption impact of chemicals in nasal cavity, the good way of the evaluation is to analyze the physiologically based pharmacokinetic model. And by using this very simple governing equations, generally speaking, we can analyze the scalar dispersion transportation in airways and also the tissue dose of chemicals. And then using this model, we integrated this PBPK model into airway, a numerical airway model, and analyze the transient phenomena of scalar dispersion in indoor environment plus inside respiratory systems. This is the outline of the numerical simulation. And here, I would like to point out very important previously reported achievements as shown in this left-hand side slide. Horizontal line of this results show the enthalpy from low to high. The vertical axis shows the acceptability and percentage of dissatisfied. And based on this research, we can say the enthalpy of indoor air will affect odor perception. And as the enthalpy of indoor air increases, acceptability decreases and percentage of dissatisfied increase. Therefore, in order to analyze the tissue dose of chemicals in nasal cavity, we must conduct the integrated simulation of heat and mass transfer, including the water vapor pressure. Okay, I would like to skip. Okay, this is the demonstrative results of the test conditions of perception. And this is the transient acetone concentration distributions. You can see the clearly heterogeneous and transient scalar concentration distribution just in the breathing zone conditions. As shown in this slide, during the inhalation period, at the vicinity of the nose opening, a potential flow will be generated, formed, and then the clean air at the upper side of the air is inhaled at the top of the nostril. And then the fresh air is directly transported with the Quanda effect to the olfactory region. I'm talking about the inhalation period. And exhalation period, where mixed acetone concentration is flow back to the lower part of respiratory system to the upper part, and then relatively well-mixed acetone will be transported to the olfactory region in nasal cavity. And furthermore, because of the differences of flow resistance in right and left and nasal cavity, we can calculate the clearly different airflow rate in left and right nasal cavities. Okay, this is a result of the equilibrium concentration at the acetone concentration on mucous layer, especially I'm talking about the olfactory regions. From this is horizontal axis shows the time passed from the test start, and including the 1, 2, 3, 4, 5, 6 breathing conditions. Please take a look at the first breathing conditions. This computer-simulated person inhaled relatively low concentration because of the well-mixed air will be inhaled via nasal nostrils. And from second breathing and third breathing, we can confirm the almost equilibrium concentration at the epithelium tissue surface concentrations. And I would like to overlapping the results done by Professor Georg Clausen, 2000. And you can see the vertical axis of left-hand side, it shows the acceptability scales. And this maybe experimental results shows adaptation of the olfactory region, olfactory cells. And just I would like to say it within 5 or 6 breathing, olfactory tissue will reach some equilibrium adaptive conditions. Therefore, I would like to say 1 sniffing or 2 sniffing is really important test conditions, but I'm not sure about 3 or 4 or 5 is enough or too much for estimation. And this is a time series of the acetone adsorption flux on mucous surface, especially I'm talking about the olfactory regions. And horizontal axis shows the time series from 1 breathing, 2nd breathing, 3rd breathing. And vertical axis shows the adsorption flux. And I would like to say 3 points. First one is our first breathing cycle. We can see very small adsorption flux on the mucous layer. And from second breathing, we can divide into 2 parts, inhale period and exhale period. This red line shows the adsorption flux on olfactory regions, and other gray line shows the other regions of respiratory systems. We can see 2 peaks, red 2 peaks during 1 breathing. This means the first peak will be transportation of also nasal pathways, and second peak will be show the retronasal pathway of the peak. Only olfactory region shows these 2 peaks, and there is no second peak in other respiratory regions. This might be some how can I say characteristic of the epithelial region, olfactory region. And if we change the target chemicals from acetone to acetic acid or ammonia, we can see clearly different adsorption flux on the mucous layer. And in case of the acetone and ammonia, we can see 2 peaks during 1 breathing. But in case of the acetic acid, we can see only 1 peak during the inhalation period and no peak during the exhalation period. It's strongly dependent on the type of chemicals. Okay, if we change the sniffing period, this is the comparison of breathing cycle and sniffing cycle. Breathing cycle is general breathing conditions, and sniffing cycle is the deeply and a bit first inhalation and long exhalation. And we can see significant differences of adsorption flux on the mucous layer. Especially in case of the sniffing cycle, the total amount of adsorbed acetones on the tissues will be 1/5 of in case of the breathing cycle 1/5. And this might have some impact of the perception of these chemicals. Okay, this is some contribution ratio analysis of acetone distribution inside the respiratory systems. And left-hand side bar shows the total inhalation of acetone, and 28% of acetone will be exhaled to the indoor environment, and 40% of inhaled acetone will be absorbed on mucus, and 55% of inhaled acetone will be reached to the alveoli region. This is the distribution of the inhaled acetone, inhaled acetone during one breathing. Okay, this is the results of the hygrothermal transfer analysis of respiratory systems. And in case of the water vapor transportation, we can see the significant differences compared to the acetone adsorption flux, because the exhalation period, the air from a lower part to the upper part will be almost saturated, and there is no emission, water vapor emission inside the respiratory system. But in case of the inhalation, relatively low relative humidity air will be introduced, and then the hygrothermal transfer from the wetted surface to air phase will be occur. Okay, this is the conclusion of my talk. First one is the bioeffluents originating from the skin surface and from exhaled air may form different concentration distributions around the human body. If my numerical simulation has certain accuracy. At present, adsorption flux of chemical compounds and sensible latent heat flux to olfactory epithelial tissue may be analyzed quantitatively, but their combined effect on acceptability and perceived odor intensity evaluation could not be analyzed so far. And olfactory fatigue is also numerically unpredictable, and also the adaptation is not predicted here. And therefore, in silico human model, computer simulated person cannot yet be used for odor assessment, and we need to conduct subjective evaluation. That's all my talk. Thank you very much.
Thank you. There is time for one of two questions, either for Kazuhide or for Pavel. Arnold?
Yeah, you said your numerical simulations could not, yeah, that's for Professor Ito. Your numerical simulations could not give conclusions about odor perception or replace subjective evaluation, but can they be used to optimize the procedure, the testing procedure, and to give more specific instructions to how the test persons should conduct the test to have most reproducible results?
Thank you very much. In my understanding, especially for the exact setup, I'm talking about the relative setup of the funnels, emission funnels, and position of the nose is very important. And then by using these types of simulation can show some appropriate relative position of funnels and nose. Yes, this is just a supplementary information for subjective evaluation. Yes, supporting information. Thank you very much.
Oh, there is another question, please.
Well, thank you both for the interesting talk. I have a question for Pavel first. The question, last slides you showed the many compounds you identified, in the experiments. Were you able to actually relate certain, like what are the most significant compounds that relate to the perceived air quality among those you identified?
The results that I show at the very end are the preliminary results of the traditional GCMS analysis that was accompanied together with the sensory perception in an attempt to characterize the atmosphere or the air quality in order to identify maybe some type of pollutants or maybe some parts of the chromatograph that would be explaining the effects of the air quality that we see. Now, recently we performed much more sophisticated measurements using proton transfer reaction mass spectroscopy with time of flight, in which we basically were able to identify which types of pollutants were actually removed by the air cleaners that we were testing, and at what was the effect of this removal. So basically what we determined is the chemical clean air delivery rate, I would say, so for the different pollutants. And now we are in the process of analyzing those results in order to be able to identify the pollutants which, first of all, may have a sensory effect on humans, and secondly, for which the strongest effect of the removal was obtained for those gas phase air cleaners. And what we want to do is we want to compare those effects with the effects that were seen on the sensory perception and see whether we can identify the pollutants that would simulate or emulate or predict the effect that we see for the sensory perception, and perhaps use those pollutants as the surrogate for the effects of on the air cleaner. So in other terms, if the clean air delivery rate that was determined through the chemical analysis is comparable with the clean air delivery rate that is determined by the sensory perception, we can probably use those pollutants for which the same effect is obtained as a surrogate for the sensory perception. But that would, of course, require several iterations and many tests. But this is our overall goal. Our overall goal is to step back from the sensory perception and use some sort of a surrogate pollutants to be able to use them in the performance testing of pollutants. And at the same time, Professor Ito, who showed, is working on basically creating a digital twin, right? Because it's a digital twin subject, right? And at that time, the development cannot be, we cannot actually predict that. But what Arnold was saying is we can learn much more on how to advance our sensory measurements. And maybe by advancing the sensory measurements, we would be able to maybe better select our subjects and have much more reliable and repeatable measurements from the sensory. So, so there are those efforts that are hopefully in the near future, we will be able to do both, have a surrogate pollutants and have a digital twin subject.
Oh, okay, thank you. Yes,
Sorry.
but we have a discussion after lunch, so we can continue. Okay.